to be finding the change of the availability of the air as it goes through it and calculate the second law efficiency from that. And let's calculate the change of entropy. We know we're going to need that. And so S2 minus S1 is equal to C sub P times the log of T2 over T1 minus R times the log of P2 over P1. S2 minus S1 is equal to 1.0047 times the log of T2, 433 over 293, minus 0.287 times the log of 400 over 120. And if I do that, we get that S2 minus S1 is equal to plus 0.0469 kilojoules per kilogram degree K. And I can calculate m dot T0 delta S as 15 times 300 times 0.0469. And so this is equal to 211.05. And this would be kilowatts. And now what we're going to do is we're going to calculate the change of the availability. And what we have is we have all the terms we found already. So I'm going to, we can just substitute in, which is why I did that. So if we go back and use the availability equation, m dot times psi 2 minus psi 1 is equal to m dot times h2 minus h1 plus v2 squared times v1 squared over 2000 minus t0 times s2 minus s1. So you'll notice that if I multiply the mass flow rate in here, I get the work, I have this term, and I have this term. So this m dot T0 is this term. I have all the terms that I did on the first law analysis, so I can substitute those in. So this term, for instance, is 2110. This term is plus 33.75, and this term is minus 211.05. So m dot times psi 2 minus psi 1 is equal to 1932.7 kilowatts. And with this and the work, we can determine the second law efficiency. So eta sub 2. So eta sub 2 is equal to the mass flow rate times the change of the work potential of the gas over the actual work that was required. So this is, we found the change of the work potential in kilowatts. We know the power required, and this will give us this. So this is 1932.7 divided by 2143.75 is equal to 0.901. So the second law of efficiency for the compressor is this. What about the adiabatic efficiency? We introduced adiabatic efficiency. So that example 9.8 did it for a turbine. Now we're going to do the same thing for a compressor. So now let's look at what would happen on this TS diagram. We're going from pressure 1 to pressure 2, P1 to P2. So we're going from there, and we're going from here up to, so from 1 to 2. And then we have 2S. So that's the reversible adiabatic process. So if I look at the compressor efficiency, so eta sub C is equal to H2S minus H1 over H2 minus H1 is equal to C sub P times T2S minus T1 over C sub P times T2 minus T1. The C sub P's cancel out. So what I need to do is find this temperature. It's a reversible adiabatic process to the same pressure, so we can apply the reversible adiabatic laws from chapter 6. And we have that T2S is equal to P1 times P2 over P1 to the K minus 1 over K. I'm going to substitute in. And so we have 293 over 400 over 120 to the 0.4 over 1.4. And if I solve for that, we get that T2S is equal to 413.3 degrees K. And the second law of efficiency, the compressor efficiency, is equal to 413.3 minus 293 over 433 minus 293. So this compressor efficiency is 0.86. So the compressor efficiency is less because we're saying, I don't care about using this work potential the way the second law of efficiency does. We're just saying, this is the best you can do, so do that. If you don't do it, we're going to ding you in terms of how well we rate this compressor. And notice that this temperature, the actual temperature here, is 433. And H2S is 413. So we can see by the temperature what the somewhat a measure of the extra work that we have to put in to make this happen. Now for homework, so you don't see me do all the work and you don't do any, now it's time to change the scenario here. So the last problems in this chapter, in chapter 9, are the following. 938, 940, 955, A and C. And so with that, that concludes chapter 9.